so my name is Ben Alberts, and I'm the group leader for Group 1 for the vapor compression refrigeration / heat pump experiment. Little introduction. We're going to conduct this experiment to perform a heat analysis, an analysis of a heat pump's performance. Heat pumps are used to take heat from a cold space and put it into a warmer space. Doing this experiment, we could use these values as engineers to maximize the efficiency and help create safer devices. Our goals are to learn how to perform an analysis on a heat pump, specifically find the coefficient of performance of heat pumps and describe the cycle we're doing on a pH diagram. So a little background. The refrigeration cycle uses thermodynamic principles, specifically the first law of thermodynamics, to remove heat from cold spaces and put it into warmer spaces. The COP refrigeration cycle is the ratio of heat loss of the cold space to the work done by the compressor, and that's actually we'll call it a typo. The Q cold is supposed to be the heat removed from a cold reservoir, and the Q hot is supposed to be the heat rejected to a hot reservoir for a refrigeration cycle. But also in an ideal system, this equation here, this could be used if the system was ideal, which obviously is not real, but if it was, instead of using the heats of the hot and cold reservoirs, we could just use the temperatures to find them. But in an ideal system also, the expansion and compression processes would be isentropic and there would be no energy loss. So here are our diagrams of PV, TS, and pH diagrams. So the 1 to 2 going up is the compression. 2 to 3 is going to be your isobaric heat rejection. 3 to 4 is your isenthalpic expansion. And then 4 to 1 is your isobaric heat absorption. So this is our apparatus. We have our compressor, condenser, evaporator, our reservoir, 2 water pumps. We have our manometers, pressure controller, coolant accumulator, cooling filter. We have our TXV, which is our expansion valve, which I'll get into next slide. Liquid separator. We have water flow sensors, coolant flow sensors, temperature sensors, 2 pressure sensors, and obviously our refrigerant, which is R134A. So this is our thermostatic expansion valve. So what it does is, it's basically like a throttle or a nozzle, you can think of it like that. The valve, what it does is it holds back high pressure refrigerant coming from the condenser, and it regulates how much can go to the evaporator. Overall, it decreases the pressure in the system, and that allows the refrigerant to boil at lower temperatures. How it specifically works though is you have your sensing bulb up there, which has refrigerant in it, so that detects the temperature of the refrigerant coming through it, and if it's hot, it'll heat up, boil, create pressure going through the capillary tube, which goes into the top of the expansion valve, and then that pushes down on the diaphragm, which compresses the spring, allowing more refrigerant to pass through, and that'll just keep balancing out as the temperatures change until it reaches a state of equilibrium, having the right amount of refrigerant flowing through. So procedure for test 1, the goal is to determine the inlet power, the heat produced, and find the COP. So first we start the TRC-VC software, switch on AV1 and AV2, which turns on the evaporator and the condenser, and we set the water flow to 5 liters per minute. Then we switch on the compressor, set an approximate value of 40% and wait for it to stabilize. We measure the values, and then we put it in a table that was given in the lab manual. We record these values, which is the power consumed, inlet and outlet temperatures, and the water flow at condenser inlet. Procedure 2, what we want to do with this is to show the compression cycles on a pH diagram and then compare that with an ideal cycle. So we start the TRC BC software, turn on the AV1 and the AV2, again, the evaporator and condenser, turn on the compressor and set it at a value of 40%. Then we adjust the evaporator, set heat exchanger flow rate to be 3, 4.5, and 6 liters per minute for the 3 different trials, and then we allow it to stabilize each time. We record the values of the cooling pressures at the inlet and of the compressor and the outlet of the condenser, the cooling temperatures at the inlet and outlet of the compressor, and the cooling temperature at the outlet of the condenser and at the outlet of the expansion valve. We do that each time for each case. And then we use these values to find enthalpies, which we can then create a pH diagram with. In conclusion, uncertainties, there's more than 10 different sensors used in the whole apparatus. So all of them probably have some kind of documented accuracy, which could lead to plenty of uncertainty in all of the values. So that's our COP. If we break down that equation that I showed earlier, that it just ends up being H1 minus H4 over H2 minus H1. I predicted the COP to be around 80%, but give or take about 5%. In an ideal cycle, obviously that COP number would be a lot higher, but it will not be ideal. There's going to be entropy, and there will be other losses because our devices just aren't perfect. But engineers can use these COP values to just figure out where problems are and continue doing research to improve these things and hopefully make better cycles in the future. And here's my references.